L is connected to C, I, oh my god, and H, no one's helping me, thank you, and D is connected to K, H, and B. And finally, C is connected to L, G, and A. Alright, look at this crazy nightmare. This might be called the alien graph. It's either called the alien graph or the spaceship graph. I don't know. It's like in gossip. It's almost like, alright, so, question, is this planar? I would be pretty damn shocked if this graph were planar. And I think, wait. It just, actually, is it? Whoa, you think it is planar?
If the chromatic number is 3, then it's planar. Is that how it works?
No, we didn't learn anything about chromatic numbers yet.
Okay, I just looked at the book.
Good. Wait, I don't know the answer to this, but what I do know is this looks pretty hard. If only we had Matt Damon to just walk in here and to just get the answer somehow immediately. Or we can do something called using interactive geometry software. Please turn the lights off, pull down the screen, move the camera, and all of those things. And I shall open this thing called Geogebra, which we should be using all the time. And I will now make this thing. Okay, now Brain over here, you would just do this for me. I think if I do this correctly, it'll, yeah, good. A, B, C, D, E, F. Can you look through the, is it like coming through the camera? G, H, I,
it's a little small.
J, K, and L. Okay, now I just have to make all the things. This is going to be really annoying, but should have just gone straight to this. Whoa. C goes to A, C goes to G, C goes to L, A goes to G. Oh, you know, before I do that, let me do all these opposites. A goes to J. This is riveting. I goes to B. Someone sing a song. E goes to...
What sort of song?
No.
K goes to G, K goes to... Someone like error checking this with like a book and stuff?
I'm like looking at the thing.
Okay, we have to, everyone needs to contribute, otherwise we will fail.
J goes to
J, D, L goes to
I and H.
C, I, and H, so C, I, and H, and D goes to
E and H.
B,
H and K.
H, K. And then D, E, and F have no other connections, is that true? Wait, K, no, something went wrong.
Connected to K. It's already
Oh,
connected.
D was already connected. So, hold on. Just be careful about this. Okay. So, good. Alright, here's my graph, man. Question, is it planar?
Hard to tell. Is there a right?
Alright, well, wouldn't it be nice to be able to, like, how do I get this back? Oh man, I wish I hadn't done that. Where are my tools? Oh boy. Hey, where'd you go, tools? Okay.
Maybe right click.
Show tools. Tools. Where did the tools go? Alright, well, somewhere are all the tools that actually enable you to like do it. Oh, here they are. Okay, good. Whew. What the hell was I about to do? I forgot already. I was going to drag. Move. So now the question is, can we drag this crap around somehow so that it's like more planar or something? Anyone wanna like try? I think I need to like undo the middle first. Also, I've already made like a mockery of this.
This is like the game where everyone puts their hands in the middle and holds hands across it, and you have to human knot. Yeah, it's like a human knot.
I'm starting to think that this freaking guy might be planar after all, which is what
Still have so many lines crossing.
I know, but like, hold on. Oh boy.
We put like A, E, and C.
Anyone want to grab the mouse?
Sure.
Coming through? You see something?
No,
You just want to play?
I've played a game like this before.
I feel like I'm almost there.
I don't
Is
think
it getting better or not really?
Not as getting better.
Okay, well, the other alternative is that we might suddenly see a K33 or K5. And if we do, we can conclude it's not planar. Because, by the way, I don't know whether it's planar or not. I'm not kidding when I say I don't know whether it's or not. I probably did this problem somewhere.
I'm just gonna start coloring.
Well, we have like this pentagon right now.
Yeah, and put them in the middle, right?
Yeah.
Yeah.
All the dots are moving outside. And
All the most connected dots, put them in the middle.
H seems to be the most connected. H and G seems to be the most connected.
H and G. Wait, can someone just we need everyone in the class participating. I'm turning over the mouse to you. Can someone Google spaceship graph and then see if it's planar and see if this even is the spaceship graph? And then also, is it in the back of the book? Also, I'll search for my homework that I at one point did, but not this year, on this topic. $639. Alright. Nope, I got nothing. I can't find it. Either I didn't do this homework or I lost it.
Can we take like six very connected vertices and see
Wait, no one's Googling spaceship graph?
to each other? My phone is dead.
Alright, riveting video.
Well, G has a lot of connections. G has like 5.
What else?
G has degree 5. H has
I
degree
can't believe
5.
that you're making me Google this. There's 5 teenagers in this room. Someone has like a phone?
Solve this.
No, there's no time to solve it.
Okay.
Alien.
There's a lot of nodes with 3, and if they all connect like a
Alien graph? It's either called the alien graph or the spaceship graph. Or I'm just crazy. And it's not called that at all. Oh no, alien spaceship graph. This might just be Gossett's dumbass name. That could be another problem.
Feels like I'm going somewhere now. I contain some I got some points in the middle. Like this.
I get too many results about extraterrestrial aliens.
Yeah, okay.
That,
Okay, he does call it the alien spaceship graph, but it's not, it's in quotes, which leads me to believe he's just doing a gossip, and I don't think this is a real name for this graph. Alright, I'm starting to think it's not planar.
Yeah, me too.
Good. Why is it not planar? 1, 2, 6, 8. Could it be as simple as, where is the K33? Hold on. I need some.
I've been trying to find one, but it's hard.
It's hard.
Oh no, wait, maybe it's not hard because you can do the
Yeah, these
you can do the
outside
shape
ones.
things, right? So you can go
Yeah, that's
through
right.
and
That's
outside.
right. Yeah, that's the whole point.
Yeah.
So
let's see.
So wait, do you see some vertices of degree 3? There's a lot of them, right?
Yeah.
So So any vertex of degree 3 is like a candidate for it. Can I jump in here?
Yeah, all right, so let's do D. I just picked D arbitrarily to start with.
Alright, so let's color this
I guess we should just make it
red.
as easy as possible. Do BH.
I'm going to color this blue. Then I'm going to color blue. What? Oh, it's already blue. Then, alright, so I don't want this 4 here. Oh, I don't know what to do. Maybe I'll ignore I and J and just color this. Oh shit. Maybe I want a K. Maybe I want K5. Maybe there's a K5 here.
And one last red that connects to all of them. So what connects to
I goes here.
what connects to K and
All right. Well, if you're really smart, you
Okay,
can
J.
find the answer to this problem.
yeah, I got it. I found a K3. I think maybe.
Really?
Yeah,
How?
Yeah, you got it. D, F,
Yeah.
J, B, H.
What are the
So
three-
Your 3 are D, F,
D, F,
J.
D,
D, F, J.
D, F, J are one set.
D, F. Can you like zoom in and stuff so people at home can see? D, F, and say it again.
J
J
are one color.
are green.
And then,
B, H, and K are the other
yeah,
color.
B, H, and K are the other color.
Let me put this back to be blue then. One more time. The
B,
three.
H, and K.
B,
B,
H,
On the top, yeah.
and
K.
Is that on the bottom?
K. Okay.
Yes.
Let's try to make some
Okay.
sense of this nightmare. Aha! Yeah, man, he just did it. Good. This is what I was hoping would happen. H, B, K, D, J, and F.
J
This
and B
is-
has to go through A.
Clear as day that these. Now I'm just gonna like all the things
So
that are
what-
like irrelevant. I'll
No,
just like move.
it does need to go through 2 others. Put G.
What? Why?
Put G in
H
between
goes
F
to
and
no,
K.
but H goes to F and F, J, and D. B
Uh,
goes to because B doesn't
Yeah,
go
B
to
doesn't
J.
So you gotta put
Uh,
A in between B and J.
Okay, hold on. H, B, K. This is riveting video.
Yeah.
D connects to all 3 of them, as you can see by this is all getting recorded.
Yeah.
Yeah.
J goes to only 2 of them. F goes to only 2 of them.
Yeah.
But we are going to be saved because G lies halfway between F and K.
Yeah.
And what lies halfway between, who's the other one that doesn't connect? J
A.
and B is like I
No, A.
or I.
You can use I and L.
Oh, you're right.
But the other is
A.
like I and
A is
yeah,
like
A is.
Okay, so now I've decided that it's I, C, E, and L that are just like totally irrelevant to the conversation. And here is the situation. What I got here is a freaking K33 hiding in plain sight for anyone to see. And what I'm now going to do is make this thick. Is this like coming out through the video?
Yeah.
And then
This is where it must be really helpful.
thick. The touchscreen would be really helpful. Can't believe you're complaining about this beautiful technology that we've had only in the last few years. Euler would kill for Geogebra. Okay, and then K is connected directly to and boom, boom. And so, and now I just go to this one and this one. Okay, so now, I don't know how clear this is going to be at home, but what we got here is K3, a graph which is homeomorphic to K33 as a subgraph. And in fact, we could even just like delete these things over here. I hesitate to do this, but if I delete all of these points, and the lines connecting them will delete as well, then it will in fact construct the subgraph. I don't know how to do that. Well, I guess it's like a delete
There's a
button.
trash can.
Boom. Ha-ha! Now, maybe even, oops.
Deleted that.
Now, it's even more obvious that I just made a subgraph of this alien spaceship graph, and it is homeomorphic to K33. Cool?
Cool.
Woo! That took just twice as long as I hoped it would, so standard discrete math time frame. While we have this homework up, let us do some of these isomorphism homework problems. So from the also homework due today, from the previous section, was a bunch of problems that were like similarly very challenging for which software would be really nice. And one of them was, what was like the hardest one? Did I sign 11B? Yes? Or 11C or 11A, which one? 11B and C. Which one was harder? Well, let's just delete everything. We don't need this for any particular reason, do we?
No.
Okay.
Delete. Okay. What's no one's helping? Good job, everyone. All right. Scoot back. Going to the homework. Nice Hamiltonian cycle we got there. The homework due today was. Indeed, he's right that I signed both 11B and 11C. I think 11 maybe B is harder. I don't know. What do you guys think?
I don't know.
Good. Good. Love when this happens. It's the pinnacle of my teaching career. Well, let's do it. The only way I can think of to do this is to just do it, man. Please, everyone, get yourself a Gaussian and look at page 623, and we're going to do 11B. The question is, are these two graphs isomorphic? And the answer is, how the hell am I possibly supposed to know? This is so hard. Well, the robot apocalypse is coming, so you better get good at this. G, H. I got one graph, which looks like this. Cha, sha, 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 sha. D goes to E, E goes to G, G goes to A, and G goes to H. Someone confirm that I've correctly done this. I feel like I just like have, yeah? Okay, now on the right, I shall do other things. This is going to be more annoying. Oh, here's what I picked up this trick from Daniel Zhu. Watch this. I just kill some things that I don't need. Cha 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 cha. And now S T U V W X. Oh, what happened? That's really annoying.
Oh, it doesn't like using X and Y.
Y, Z. I must have already had an X somewhere. It's annoying. Yeah. Call that X. I hate computers. Y and Z. Okay. And Chuck. Yo.
Have arrived.
Good.
No need to panic. I'm here.
Alright. These things are the same to you.
Now I need to connect various things, in particular, cha, cha, sha, 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 sha. I don't need this. Good. X and T to W. Have I done that correctly? Okay, so what did we discuss last class? What does one do when presented with the task, are these two graphs isomorphic? Step one, you like zooming in and stuff so that people can actually see?
Yeah.
Okay, step one, do these graphs have the same number of vertices?
Yeah.
8, say yes.
Yes.
Good, do these graphs have the same number of edges?
Should. 6, 7, 8, 9, 10.
Yes. 4, 5,
Degrees.
6, 7, 8, 9, 10. I think 12. I count 12 in both graphs. Someone back me up.
Yeah.
Good. Do these graphs have the same degree sequence? Or rather, what is the degree sequence?
All
Oh, boy.
degrees.
Yeah, these both graphs are both regular graphs. These are called cubic graphs. Okay, so they either are or are not isomorphic. And now, here's what you do. Based on your just abilities, you either figure this out in like 30 minutes or never, or like 1 minute, or like, you know, that's just how it goes, man, you know? You're either Stav and you just get it in 30 seconds, or you're me and you take 10 minutes, or you're someone else and you try for 30 minutes and you just never get it and you cry. But I have done this problem before, and I think I know what to do.
Yeah, you have to.
I'm thinking, I don't know what to do.
You gotta
I
start
gotta
with
like
square.
inside out this guy.
Wait.
No, that was wrong.
Yeah, you want to take what is that? T and U.
Wait, hold on.
T and U on the
I should just let him do it. Good, hold on. Okay, that was the graph? Or did I screw it up yet? That's the
Yeah,
graph,
that's
right? Okay, let me just save this real quick. Save. And now we'll call this Isomorphisms. Save. Alright. Let me just actually like think for like a second. Here's the thing, I see a 4 cycle, a 4 cycle, a 5 cycle, a 4 cycle, and a 5 cycle. Or did I count wrong? Here.
There's 2 5 cycles.
Oh boy. Wait, I think I want to undo this one, and I think I want to manipulate the one on the left. And
those up.
oh shit, I screwed up. No, I didn't screw it up. I'm done. It's just backwards.
Uh,
Look, see? I did it. Wait, I just need to rotate this whole thing 90 degrees. Does everyone see what I mean by I did it?
Yeah.
Okay, am I smart enough to rotate this 90 degrees? I don't know if I am. F, C, A, E, D, B, F, C, A. Okay, armed with the knowledge that these in fact are isomorphic, because I've done this problem before, give me the confidence to just like go. And hold on, now I'm like, oh, I screwed up again. It needs to be upside down, right? Just switch C and D, switch E and F. Switch A. All right. Let the record show for people watching at home that I have by a series of manipulations, which if I were smart I would like just do in my brain in like some period of time. Instead, by random dragging around and hoping, I have showed that these two graphs are isomorphic. Cool? That's the best we can do. There's no algorithm. We can only just like try. Good. Who's feeling enlightened? Woo! All right. Next. I don't think we need the computer anymore, so let's turn these off. Next thing we're on now, we've done point 3 of 10 for today. Go over, I was going to go over this Hamiltonian cycle problem. I've decided that we're not going to do that. There was because I suspect that you guys, it seems to be happening without me asking direct questions, because you don't want to ask questions that you don't want to hear the answers to. That's one of those things. Seems that many of you did not do your homework due today. There was a problem, last class we did, in very slow manner, this proof about a sufficient condition for the existence of a Hamiltonian cycle. And one of the problems on the homework asked you to prove a very, very similar theorem. You should do this at some point. The theorem was, this is from section 10.3 now, number 19. This was part of the homework due today, right? It was called Another Sufficient Condition for a Hamilton Cycle. And it basically said, to do this, it is sufficient for the sums of the degrees of the vertices to be greater than or equal to n. And that just is sufficient. All right, good. No one's saying any words. So either that means they don't know the hell I'm talking about, they didn't do the homework, they didn't even look at it, they don't care. So I'm moving on. It's really important, it's really hard. What?
It seems like it's basically always met if the one, or if that's met.
The sum of the degrees of the vertices is greater than or equal to n. What we did, we tried to do it 2 classes ago, and we eventually did it last class, was this theorem which says that if delta, which is greater than or equal to n over 2, then G has a Hamiltonian cycle. Of course you remember this proof, we spent 45 minutes on it,
So
literally last class. Yeah?
And since we said
Delta was
that-
the minimum degree.
Yeah.
And so we did this entire thing in which we constructed the set of all graphs with n vertices. We made the set of all of them that meet this condition but do not have a Hamiltonian cycle. We created this graph G, which had the most number of edges. We added an extra edge, G prime. I spent about 2 hours since then thinking about this problem, by the way, and now I have like a much better proof, but no one seems interested, so I won't share it with you. But essentially it went like this. There were all these vertices, and then eventually it was like dun, 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 and then you had like, you know, WK or whatever, and WK plus 1. Remember this whole thing?
Yeah.
How could you possibly forget? And then da, 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 and then okay, and then what happened was in G prime, which is the graph that one gets from adding this extra mystery edge between Wn and W1, then there's a Hamiltonian cycle. And what we need to show is that that it is impossible for this to be true because
There just aren't, if it's not true, then there aren't enough connections.
yeah, I'm not sure if there aren't enough connections. And this morning, and I had a sort of an idea that like I had a sort of a better maybe understanding of this. What was sort of to say like, look, man, there are these two. Can you give me that orange from over there? What we really did last class was to construct these kind of 2 sort of sets. We said, yo, the set that's I think the easiest to understand is the set of all the vertices which are friends with Wn. And all the vertices which are friends with Wn. Of course, Wn is not one of them, so I'm just going to add this extra circle here. But this is supposed to be all the people in the Hamiltonian cycle that are friends with Wn. This set we called B. And then we said all the people who are friends with W1, we put in this other set, F. Okay, but it's not quite true that it's all the people that are friends with W1. Because what we actually care about is like, is there sort of 2 consecutive members of this Hamiltonian cycle in G prime, such that one of them is friends with Wn, and the next one is friends with W1. And that can't be. This is just another repeat. This is the 3rd class in a row we're talking about this proof, right? You can't have someone who's friends with Wn, and the next person in the cycle be friends with W1. Because if that were the case, then you could circumvent this W1 friendship and start at W1, go until you get to WK, then go from WK to Wn, reverse this process backward to WK plus 1, and then go back to W1. And if you could do that, then there would have been a Hamiltonian cycle in G, but by assumption there's no Hamiltonian cycle in G. Therefore, there can't be this situation where there's someone who's friends with Wn and the next person's friends with W1. And so the sort of casual way of doing this proof is you kind of just take people 2 at a time and kind of like scooch along this Hamiltonian cycle. And you ask every 2 people, like, hey, first person, are you friends with Wn? Hey, second person, are you friends with W1? And they can't both be true, right? If they're both true, you have a contradiction. So if they can't both be true, in every like 2 pairs going along the cycle, like you have only 1 friendship at most. adding up the friendships of the first one with Wn and the second one with W1. And if you do that, what you end up with is just that there aren't enough friendships, right? And then you just violate the condition. And what we showed was, I even just like wrote this out a little bit more, right? What can't happen is we can't have, so that's like my sign for no, it can't be true that there's a WK, WN edge and a WK plus 1 W1 edge. Okay. That's kind of what I just said, right? And so what you do is you just, I don't think we need to do this again, but what you do is you go through this, what you go through and what you end up with, what we ended up with last time, was the degree of Wn plus, our contradiction was the degree of Wn plus the degree of W1 was less than n. That was our contradiction. And it contradicted because we know that since the degree of any vertex has to be greater than or equal to n, then that's false. And so, okay, looking back on this whole proof, what you were supposed to do with given this homework assignment is realize that actually a weaker condition is possible for this theorem. It's not actually, we don't actually need everyone to be friends with half of the people. All we need is that for any two people, together they have to be friends with n people. Because in fact, we used everyone friends with two people just to show that it's impossible for the step in the proof that we got the contradiction was this step, right? And so in fact, the theorem goes through with the weaker condition. Instead of, I replace this, it's the exact same theorem, but I just replace this assumption that delta is greater than or equal to n over 2 with a weaker, strictly weaker assumption. The assumption that for any two vertices, like V and W, that the degree of V plus the degree of W is greater than or equal to n. And with this weaker condition, we still prove the theorem the exact same way. And does everyone see what I mean by it being weaker? It's weaker in the sense that if this implies this, right? So then this is a weaker term. Okay, I was going to do this whole game where I planned this whole thing. We were going to like have a ball and pass it around and act it out. But you guys don't seem excited about that, and we don't have time, so we're just going to forget about it. I'm just going to make a mental note to do this next year. Woo! All right, good. We have now hit point, I don't know, 6:15, numbers 10 and 11. Oh, number 10, there was this problem that asked, is there a Hamiltonian path in this graph? And the answer was, this is number 10 on page 615. The answer was no. And we were going to talk about that, but you guys don't seem to care, so screw it. Good. Shall we go to like the real thing of today? We got 20 minutes.
Yeah.
All right. So there are these things. Grab the camera. I guess we're just going to talk about the